Okay, welcome back to the second part of this fourth lecture. So now we're going to look at the linearization of a nonlinear dynamical system in continuous time. So again, our task is to do something like that. So I have the nonlinear system, okay, and from that I want to write down the linearized version of it. Okay, so that's the idea. Now let me give you a quick reminder of what we call Taylor series expansion or approximation of a function. Okay, because we're going to use that. So let's first of all imagine a very simple function of just one argument. All right. So to do the approximation, we choose a particular value from the domain. Okay, we choose a particular x value within x, and then this is the general formula of Taylor series approximation, right? You might remember that. First, I evaluate this function at that point. Then I take the first order derivative and evaluate that first order derivative at that point, and then I look at the deviation of x from that point, right? So this part approximates the function in the first order. Then you can add the second order derivative. Of course, when you add the second order derivative, you once again evaluate that derivative at x bar, but then you scale it down, okay? And then you have the quadratic deviation from that point. Then you have the third order approximation, then the fourth order, fifth order, and that goes on, okay? So here, if the order of approximation, let's say k, goes to positive infinity, then your approximation goes to the function itself, okay? I can actually draw a figure. Suppose that you have this nonlinear function, okay? Then you choose a point, let's say this point here as x bar, and then you take the first order derivative. Oops, not good enough. You take the first order derivative, okay? The first order derivative is this, so k is equal to 1. You can do it for a second order derivative. Oops. You can have something like that. Okay. And obviously, if you increase the order, you might have some better results. But if this function is originally quadratic, the quadratic approximation will work just fine. You might have different types of examples. Imagine that you have this function, right? X, f of x. Let's say you choose this point. Now, of course, in this point, if you take a linear approximation, you have something like that, right? Not very good. You can have a quadratic approximation. So maybe it will be something like that. Okay. You can have a third order one, so which can be perhaps something like this. Okay. And that goes on. If you increase the order, you of course approximate the function better and better. Now realize one thing that is important. If you move away from x bar, then your approximation error increases, right? That's important. if you move away from your reference point, your margin of error basically increase. Okay. Now let me go back to here. Now, if your function has more than one argument, you can still do the same, right? Suppose now that your function has n arguments, right? First, again, you evaluate the function at that x bar. Now, x bar is of course x bar 1, x bar 2, x bar n, right? Then you keep on doing that for all arguments, okay? x3 bar plus, and that goes on until when? Until you have fn prime x bar xn minus x bar, and obviously, so x bar n. Now, obviously, what you have here is the first order, right? Now, here n is some positive number, but k is just 1. Because I am looking at first order derivatives. Okay? So this is the first order Taylor series approximation of this function. And this is what we're going to use, right? Why? Because we want our nonlinear system to be a linear one. Okay? We want to transform our nonlinear system into a linear system. For this reason, we're going to use first order Taylor series approximation. Okay? Our approximation order will be just 1. So let's just do that. Example. So let's write down a 2x2 system. Okay. So your x dot, let's say, is equal to x2 square minus 4yt plus let's say 16, and yt dot equals, let's say, natural logarithm of yt, let's say, let's put a minus here, plus xt minus, let's say, 4. Let's see if there is a steady state. Okay. For this function to have, for this system to have a steady state, I have x squared minus 4y plus 16 equals 0, minus ln y plus x minus 4 equals 0. Is there a steady state here? Well, I think we cannot solve an analytical solution here. We cannot find an analytical solution here. So what can we do here? Let's look at this. Okay, let me find some examples, some working examples. Okay, I already have the notes. So I can find a certain example here. Just a sec. Sorry for waiting you. I have some exam questions somewhere here. So, okay. That's all right. So Where are they? Sorry, guys. I am pissed right now. Okay, I cannot find them. One final check. Oh, okay. I think that works. I think I just found it. Yeah. Okay. So let's try this. Let me open some space here. Forget about this because you cannot always find. You're still there, by the way. Okay. You have to work out the examples before coming to class, right? Okay, but let's try this. So this is let's write that. Okay, so this is 6xt minus yt square plus 10 and yt dot is equal to xt square minus yt square plus 3. So if I'm not mistaken, there is a steady state, and we can now just do it. Okay. Yes. So by definition, the steady state requires this, right? So we have 6x minus y squared plus 10 equals 0, and x squared minus y squared plus 3 equals 0. So from the first equation, I realize y squared is equal to 6x plus 10. So then I have x squared minus 6x plus n plus 3 equals 0. So I have x squared minus 6x minus 7 equals 0, right? Now realize from this is that there are possibly two steady states, right? Out of this system, you can have two, let's say, steady states, right? You have 6 plus minus 36 minus 4 times minus 7, so it's that, right? Divided by 2. Okay, so this is okay, let me just check. Yeah, so this is 6 plus minus 8 divided by 2. So you have xa equals 7, xb equals minus 1. Is that correct? Yeah. So then, for each of these values, of course, you have YA and YB, right? So YA is equal to 52, YB is equal to 4. Is that correct? No. Okay, of course. Square root of 52 and square root of 4. Okay, and then you have YA1 square root of 52. Then you have YA2 minus square root of 52, right? You're going to be careful here. YB1 plus 2, YB2 minus 2. Okay? So there are different steady states, right? Different steady states. So set of steady states, if you want to write it, the set of steady states, if you want to write it, is something like that. So you have 7 when x is 7, you have square root of 52. Then you have 7 minus square root of 52, right? Then you have minus 1, 2, and you have minus 1, minus 2. Okay? Let me just check. Yes. Okay, so these are the set of steady states. Again, you define the set of steady states by a typical element x star y star such that x dot will be equal to 0 and y dot will be equal to 0. Since there's a quadratic formula here, your steady state points are several. All right. Now, what we want to do, of course, choose one of the steady states and to linearize the system around one of these steady states. Okay. So let's just do that. So once again, the system is 6x minus y squared plus 10 and 6x squared minus y squared plus 3, right? Let me just check. Yes. Okay. Now we want to linearize these functions, right? Let's denote this function. Let's say fxy, and we can denote it by gxy. So my system is x dot equals fxy, y dot equals gxy. Okay. Now let's choose the point, the steady state point minus 1, 2. Okay. So this is our, let's say, x bar. So x bar is equal to minus 1, y bar is equal to 2. Okay, so we want to linearize both of these functions around these points. Now remember, first of all, I want to evaluate the function at this point, right? I want to evaluate f function at x bar, y bar. Then I have the derivative with respect to x. Okay, again evaluated at x bar, y bar. Then I have x minus x bar. Then I have the derivative with respect to y evaluated at x bar, y bar, and then I have y minus y bar. Okay, so let's do it. Now by definition, this is 0, right? So if you write it, 6 times minus 1 minus y square is 4, right? Plus 10. This is that. And by definition, it is 0, right? Because it is the steady state. In the steady state, this is 0. Then you have the derivative of the function with respect to x. What is that equal to? It is equal to the derivative of this function with respect to x is just equal to 6. All right? So this is that. Times you have x minus x bar. And what is your x bar? Your x bar is -1, so you have +1 here. Okay? Plus the derivative of this function with respect to y, which is equal to -2y, right? The derivative of f with respect to y is equal to -2y, and your y bar is equal to 2, right? So you have y minus y bar. So if you want to rewrite it, you're going to have something like this. So this is 0, this part, right? -4, -6, plus 10, this is 0. Then you have plus 6x plus 6. Then you have -4, right? This is y is equal to 2. So this is y bar actually. So y bar is equal to 2. So it is -4 times y minus your y bar is 2. So you have 6x plus 6 minus 4y plus 8. So you have 6x plus 4y plus 14. Okay? So that is your x. So let me check whether it is correct, because I have the solution here. Yes, this is
Hocam
so,
minus 4y olması gerekmiyor.
Evet, this one will be -4. Oops. So 6x. 6x plus -4. Okay, now let's do the same for the y function. Let me use this space and do it very quickly. Okay, let me use a different color. So now gxy equals 0 plus, right? This will be 0 in the steady state, right? Square of -1 is equal to 1. This is -4 plus 3 is just 0. Then you have the derivative of this function with respect to x. It is equal to 2x. Evaluated at x bar, it is 2x bar. X minus x bar plus the derivative of this function with respect to y. It is -2y. Evaluated at y bar, it is -2y bar. Then you have y minus y bar. Okay? So you have 2 times -1, x minus -1, it is +1, minus 2 times 2, y minus 2. So you have -2x minus 2 minus 4y plus 8. So you have -2x minus 4y plus 6. Is that correct? No, it is not correct. I have a mistake somewhere. No, do I have a mistake or not? So let's check. 0, okay. Then I take the derivative with respect to x. It is 2x. I evaluate it at x bar. X minus x bar plus I have the derivative with respect to y. It is minus 2y. I evaluated at x bar, y bar. So I have minus 2 times y bar. Then y minus y bar. So I have 2 times minus 1. X plus 1. That's correct. I have minus 2 here. And y bar is 2. So it is minus 4. And then I have minus 2. So minus 2x minus 2 minus 4y plus 8. Yeah, that's correct. So that's it. You have the linearized system, right? Let me write in a different color. X dot is equal to 6x minus 4y plus 14. And y dot is equal to minus 2x minus 2y minus 4y plus 6. As you realize, the system originally in the format of this is translated into this. Okay?
Sorry, is there any rule while choosing one of the steady states?
No, there's no rule. It depends on your problem. It depends on your purposes. There is general no rule if you have more than one steady state, and which is pretty important actually, because if you have multiple equilibria in the steady state, then there must be good reasons for that, right? In the story, in the economic fundamentals, there is a reason for this multiplicity of equilibria, and choosing which one depends on your choice. Let's suppose this. Suppose that you have this development model with poverty traps. In one of the equilibria, you have the poverty trap. In one of the equilibria, you have constant growth. Now, if you want to study, let's say, sub-Saharan Africa, you want to look at, obviously, the poverty trap equilibrium, right? If you want to study, let's say, South Korea, you want to study the growth equilibrium. You want to choose the growth equilibrium. So that depends on your purpose, your fundamentals, and your research question in general. There is no pre-specified rule or some rule of thumb to do that.
Okay, thank you.
So it would be a nice exercise if you do the same for the other states. But there, I mean, maybe I can send you some problem sets. Actually, you can check the website. In the website, there are problem sets and exam questions. So in those problem sets and exam questions, you're going to find a lot of different types of nonlinear systems. So you can actually practice with them. But that's the idea. So take the first order derivatives, evaluate at them in the steady state. Okay. Now, let's take a moment here. Now, if you have any questions about normalization and linearization, these are, as you see, both these are separate things, entirely separate things, then you can ask them here at this moment. We can discuss. I can clarify if you have some questions. Otherwise, I want to switch back to our discussion of stability for the linear systems, or more generally, linearized systems. Then in the next hour, I will continue with that.
Sorry, what is the difference between the normalization and linearization?
They're entirely different things. Let me explain once again. In the beginning, you have this system. Okay, this system is nonlinear. All right. Now, what you can do with this system, of course, you can find a steady state if it exists, right? And you can draw phase diagrams. You can find the arrows. You can do several stuff with that, right? Now, in practice, we want to work with a linearized version of this system. Why? Because we want to be exactly sure. Just a moment, please. So we want to make sure to tell exactly which type of dynamic equilibrium is this, okay? Whether it is is there a question in chat? Oh, okay, no. So we want to make sure we know the stability properties of equilibrium. And if we linearize the system, we can tell you exactly what type of equilibrium is this. Is it a node? Is it a spiral? Is it a saddle point? Okay. Is it a center? Etc. So in a linearized system, we know exactly what is the equilibrium point. Okay. So we can tell exactly how the system is stable or not. Then, with a linearized model, you can actually normalize it. Okay? Now, normalization means I basically move the system to make the origin the steady state. Okay? So you can do stuff like this. So if your linear system is there, okay, let's say this is a linear system, your steady state is here. Now you want to move this to here without changing the slopes. Okay? This is normalization. So this is linearization. And this is the normalization of the model. Okay? As you see, they are two separate things. They are not actually related. Okay?
Okay, thank you.
Yeah. Anything else before we start working on? Okay, sorry, I don't have a mic. I couldn't get what is the difference between choosing XA7 XP1, how it will affect our solution in matter of explanation of what we want to achieve. Well, again, this is related with an earlier question. So, that's the solution, right? So, XA equals 7 is a steady state. XB equals -1 is also a steady state. Now, for both of these values, there are two separate Y values, right? So 2 by 2 equals 4. We have 4 steady states. Now, how you can choose is not in your control. So if your system have 4 steady states, then your system have 4 steady states. Okay. Let me clarify one thing. So let me draw a figure. So I'm gonna try to create 4 steady states. 3, 4, right? So 1, 2, 3, 4. Now beyond that, this goes on like this. This goes on like this. This goes on like this, and this goes like this, let's say, okay? Now, this is a system with 4 steady states, okay? Now, depending on your research question and depending on your model, these variables will have some economic meanings, right? Then you can think about what does it mean to have a low X value as a steady state or a high X value as a steady state, okay? This is a high X, this is low X. Okay, maybe you can disregard this because here it is negative. All right. What you can learn, for instance, in this example, regardless of the x value, y values are closer to each other, right? Y values are closer to each other. But then, depending on the meaning of this variable, you may be interested in understanding a low x or high x economy. So it really depends on your question. It really depends on what you're going to do with this model. We are not particularly choosing for x equal 7 or x equal -1. I just choose one of them just to simplify, just to show you how the linearization works. But beyond that, again, it depends entirely on your research question and the meaning of these variables. Oh, there are more in the chat. Okay, let me stop sharing to see the chat. So do we need to use both in any case? Use for what? No. If you want to linearize your model, you're going to choose one of them, one of the steady states. Okay? If you're going to want to linearize your system, you're going to choose one of the steady states. Now we have less than a minute. We're going to continue at, let's say, 250, okay? At 250, we're going to continue. All right? So I'm ending this right now.
Okay, thank you.
Okay.